Hi everyone, how are you? Hi Samir. Hello Sonam. Good evening. Hi Abhishek. Hello Devesh. Okay, so let's get started. So today we are going to see more in the linear transformation, right? I mean, we have seen little bit of the linear transformation, but we will see more about the linear transformation in today's class. Okay, and why more about linear transformation? Because this is you can say this is the crux of matrices. Because the matrices work as a function. We have seen in the previous class. Today also we will see, but we have seen little bit, right? That if there is a transformation, let's suppose just a second. Yeah. So okay. So let's suppose there is a transformation T, then this transformation is equivalent to a matrix multiplication, right? We have seen this. I mean, if there is a linear transformation, for example, if there is a linear transformation T, then this is equivalent to the matrix multiplication. We have already seen this. So you can say that this T of X, let's suppose this is the linear transformation of X, it is as good as A of X, right? So you can say this matrix A, okay, whenever you're multiplying with A, it is working as a function, right? So matrix, you can understand this matrix as a function. And this linear transformation is very closely related to, the matrices as a function. I mean, this is as good as matrices as a function. So we need to understand this linear transformation more carefully because it directly relate with the matrix. Okay, that how does the matrix behaves? As I told you in the previous class also, some people call them linear mapping, some people call linear transformation, some people call linear function. Okay, I mean these are not my terms; these are standard terms. I mean, as you can see that I have taken reference from the standard university. You can call them linear function. Okay, you can call them linear transformation. You can call them linear mapping. So we will say all are same, right? All are same, as I told in the previous class. I mean, these are not my terms again. These are the standard terms, right? So as you can see, this is a standard university reference. Okay. Okay. Now we have seen this that for the linear transformation, these are the two properties which need to be satisfied, right? Okay, these kind of questions we have done. Let's just quickly do one more. I think this is the previous question only, but let's just quickly do for the sake of recap. Can you tell me which one is true and I mean which one is a linear? Is this linear? Is A linear? No, right? Why A is not linear? Because of this constant. So that's not linear because of the constant. What about B? I think B is linear. Okay. C is not linear because of this constant. It is not linear because of this sin x, right? So B is linear. Okay, cool. We have also seen that for every linear transformation, there is associated matrix A, right? Or vice versa, which means it is both ways. It is both ways. Which means that for every matrix A, there is a linear transformation. For every linear transformation, there is a matrix A. Okay, it is both ways. Is this okay to everyone? Right? So which means for every linear transformation, there is a matrix. For every matrix, there is a linear transformation. Right? So we have also seen this short trick to identify linear transformation, right? Okay, cool. That is fine. So it is just a visual representation of linear transformation where what we are trying to say that either you actually yesterday, do you remember that I was referring to the three blue one brown that particular video? Do you remember? So actually, I wanted to see this kind of visualization there. So I was just going back and forth. But yeah, so that is something I wanted to convey yesterday. But I was not. I mean, I did not find exactly that kind of convention there. So that's why explicitly I'm putting it here that you do first addition. Okay, I mean let's suppose u and v are two vectors. You first do addition and then you do linear transformation, then you will be getting this. Or you first do the linear transformation and then you do the addition, then you will be getting the same vector, right? Do you remember that for every matrix, let's suppose you have a matrix A, okay, either it is a matrix multiplication or it is a linear transpose, both are same by the way. So linear transformation. So for every matrix A, what does it do to any vector? So it was an old vector. What does it do? Do you remember? For any vector, what does it do? It either rotates or scale. Remember from the eigenvalue discussion? In the eigenvalue, I told that for every matrix, if you multiply by the vector, then it will either rotate or it will scale, right? Okay. So for example, let's suppose it is a matrix which it is rotating by theta, right? So that's fine. So you can understand logically also that it is rotating by theta, it is rotating by theta, and everyone is rotating by theta. So that's fine. Okay. And they're getting stretched and like this. Okay. Anyway, so either you do first addition and then you take the linear transformation, or you first do the linear transformation and then you do the addition. Both will be the same thing, right? Both will be the same thing. Cool. Similarly, you multiply by the vector first, and then you do the linear transformation, or you first do the linear transformation and then you multiply the vector with the constant. Let's suppose c. Then both are the same thing. Okay, cool. Tell me, is this true or false? Let's just do this question quickly. This is true or false? It is easy question. So they are saying that is a linear transformation, then zero vector must be the solution of tx equal to zero, right? So which means that they are trying to say that T0 must be 0. Tell me, is this true or false? This is true, that origin doesn't get shifted in the linear transformation, right? So that's why you can see, okay, the answer I don't have, but that's fine. I mean, this is true, right? Okay. Interestingly, let's suppose I ask you one interesting question. So I am saying if T is a linear transformation, then then I am saying, let's suppose uh, T of x equal to, sorry, T of 0 equal to 0. This is true, right? Or maybe let me say in other words that T of x equal to 0 has x equal to 0 as solution, right? This is true or false? This is true, right? Okay. This is true. Now tell me this. Now tell me this. Okay, this is true. Now let's see this. Suppose I tell you something like this, right? Suppose I tell you something like this. This is true, that's fine. But suppose, interestingly, let me ask you some question. Let me see how many of you can answer. Suppose this is the new question that I want to ask. Suppose they say that T is a linear transformation and T is a linear transformation, and let's suppose they say and T of x equal to 0. Okay. So basically they are saying T is a linear transformation and T of x equal to 0. Then does this mean that x is always 0? Does this mean this? Does this imply for some vector x, okay, for some x, tx equal to 0, T of x equal to 0, does this mean that x will be 0? What do you think? No, right? So basically what they mean to say that if ax equal to 0 is there, it doesn't mean that x equal to 0 is the only solution. Okay. There may be, if a is, let's suppose, linearly dependent, okay, vectors of a is linearly dependent, then there may be other solutions, right? There may be other solutions of this a. We will see those kind of things also, but I'm just telling you in front, right? See, these both are different examples. This is true, but this is false. Why? Here I'm saying that tx equal to 0 has x equal to 0 as a solution. Yes, it has. It will always have the solution, right? I mean, if they say that, okay, t0 equal to 0 or not, yes, this is true. But something else can also be 0, right? Something else can also be 0. Which means if they say that tx equal to 0, then does this mean x equal to 0? No. Something else can also be 0. Okay. We will see this. Okay, we will see this. Yeah, if a vector is linearly independent, if matrix A is basically, you can say the rank of A is n, okay, I mean the all columns are linearly independent, then this is true, okay. But for some x and for some random linear transformation, it may be false. I mean, need not to be true, right? Okay, don't worry, it will get more clear. Don't worry. Okay, don't worry about it. Now let's just see this. Okay, now let's just see this. Tell me, consider this linear transformation. Tell me the standard matrix of T. Okay, can you tell me the matrix associated with T? Should I recall you that what happened last in the last lecture? Should I quickly tell you that how to calculate a standard matrix? I can quickly tell in 5 minutes maybe. Okay. So see here that whenever you have a linear transformation, we say that it is as good as ax, right? It is as good as ax, and we want to find out the value of this a. I mean, what is this a, right? We want to find out what is this a. Let's suppose a is some let's suppose a1 a2. Okay. Let's suppose it has only two columns for the sake of example. Now you tell me T of even. Even is a standard basis. Okay. You tell me T of even. What it will be? So it will be A1, A2, and instead of X, I have even, which is 1, 0. Isn't it A1? Isn't it A1? T of even? Tell me. Similarly, you tell me what is T of E2? T of E2 will come out to be something like this. This is A1, this is A2, and this is 0, 1. Then tell me, isn't it A2? Right? So I'm interested in finding out the value of A1 and A2. Then can you tell me what are the values of A1 and A2? I think I think you can tell me the values of A1 and A2. So A1 is coming out to be T of E1. So that is why you can just substitute here the value of A1 and A2, which means the matrix associated with A is something like this, right? Is something like this. Sorry, this is Te1. This is Te2. Basically, if I want to find out the matrix associated with this linear transformation, it is nothing but linear transformation of the basis vectors. If I have the linear transformation of the basis vectors, I have the linear transformation completely in its entirety, right? Do you remember now that A was something like this? This is some other way to calculate A. I mean, just some other way to understand A. That if you want to calculate A, it is actually very easy. You just put T of E1. If you find out T of E1, it is coming out to be A1, right? You find out T of E2, it is coming out to be A2. And we wanted A1, A2 just. So A1, A2 is T1, T2, isn't it? Do you remember this? Let me know. Okay. Now let's just see this question. Now here they are saying find the standard matrix of T. So what is the standard matrix of T? It is nothing but it is nothing but you can say, okay, what should be the dimension of this? Or maybe you can find out here T1, T2, T3, right? Because this input is basically R3, right? So it will be T1, T2, T3. This is the standard matrix. T1 will be this is 0, 0, 1, right? Since it is 0, 0, 1, I think only at x3 it is 1, right? So only at x3 it is 1. So which means it is 0, 1. If x2 is 1, then I think it is 1, 1. If x1 is 1, uh sorry, it is 1, 0, 0. Initially it is 1, 0, 0. I'm sorry about it. So if x1 is 1, everything is 0. If x2 is 1, then this. And if x3 is 1, everything is 0, then this, right? If x3 is 1, yeah. So 1, 0, 1, 1, and 0, 1. This is the matrix that you people are also getting, right? Is this okay to everyone? Okay, okay, cool. Now, I hope you understood that how we are calculating the standard matrix, right? It is called a standard matrix. Okay. Now let's just see this question. Find the standard matrix for this linear transformation T such that this is the case. Tell me. Yes, this RHS is the standard matrix, right? Okay, 3, 1, minus 3, minus 1, and 0, 2, 2, 0, and 0, 0, 0, 0, right? This is the standard matrix. Okay, let's just find out this quickly. Find the standard matrix for this linear transformation. I think you can do it, right? This is E1 is nothing but 1, 0. So it will be minus of 1 and then 0. And then E2 is 0, 1, right? 0, 1 minus 2 of this. So it will be uh, minus 2, I think, and then 1, right? Minus 2 and 1. Okay. Okay. Cool. So actually from here also you can directly see that whatever vector we are getting, right? Whatever vector we are getting, the coordinates of that vector is ultimately in the standard basis. Ultimately it is minus 1, right? Minus 1. I mean, whatever is the factor of this, which is minus 2 and 1 is the coordinates of this vector. I mean, ultimately I want to write the coordinates. So from here also you can directly observe that this is minus 2 and 1, right? And this is minus 1 and then 0. Okay. Because ultimately this is a vector or this is a scalar, the whole thing. Tell me. This whole thing is a vector or scalar? This whole thing is a vector, right? So it is a vector. So you can directly see the coordinates of the vector. I mean, the coordinates of the vector is nothing but coordinate of E1 and coordinate of, I mean, the coefficient of E1 and coefficient of E2, right? Okay. Now let's just see this question. This is a true false question. Just try to solve this question and tell me if it is true or false. So what they're saying that if the vectors are these V1, V2, V3, right? This is in R2. These vectors are in R2. So tell me these vectors will be, since these are three vectors in R2, right? So V1, V2, V3, these three vectors are in R2. So three vectors in R2. These are linearly dependent or independent? These are linearly dependent, right? Because of three vectors in R2. Now, now you did some linear transformation, which means since these are linearly dependent, it means that there is a non-trivial solution, right? Has non-trivial solution. Is this okay to everyone? What does this mean? It means if you take the linear transformation, right? Linear transformation both side, then or the matrix multiplication both side, whatever you like to call. So it will be C1 T of V1 plus C2 T of V2, okay, plus C3 T of V3 equal to 0, right? Okay. Or maybe you can understand with the matrix multiplication, what in whatever way you like to understand. Maybe you can understand with the matrix multiplication, which is this. Or maybe see, this is nothing but A into C1 C1 V1 plus C2 V2 plus C3 V3. I mean, this is just A, right? A into V1. This is A into V2. This is A into V3. So you can take A common or something like this, right? So now you tell me, if this is having multiple solutions, then in multiple ways you can make it zero. Then can't you make in multiple ways? Can't you make whole thing at zero? Which means this will also be having multiple, you can say, multiple solutions. So that's why these three vectors, right, after multiplying by A also, these are linearly dependent. So let's just see the solution. See what they're saying. This is having a non-trivial solution, evaluating T on the both sides using the property. So finally you got this. Hence this set is linearly dependent. Why? Because uh, see, they are saying that if this is having non-trivial solution, then after linear transformation also you will be having non-trivial solution. How you can see this directly, instead of involving A or something? Yeah, I think we can understand with A. So if there is some combination of x1, x2, x3 that is making that 0, then the same combination will make this also 0, because you just multiplied by A, and you can always take that A outside, right? Yeah. So you can say that if there are, let's suppose if there are multiple solutions, let's suppose 2v1 plus 3v2 plus, let's suppose, or minus v3. If let's suppose this is making 0, right? Then for every of this solution, for every of this, what is the solution of this? 2, 3, and minus 1, right? For every this, you have non-trivial solution of linear transformation also. Because in linear transformation, you are doing nothing, but you are multiplying by A. So if this is having non-trivial solution, then this is also having the non-trivial solution, right? Okay. Now let's see one small topic. It is not even the topic, but yeah, let's take it as a topic, which is composition of transformations. For example, if you are you familiar with this kind of notation, by the way? Composition notation, composition of functions. For example, if there are two functions, let's suppose f and g. Okay, fx equal to, let's suppose, sin x, and gx equal to, let's suppose, x square. And if I ask you f of, g of x, then what it will be? It is sine of g of x. G of x is x square, so it is sine of x square, isn't it? So basically this is called composition of functions, right? This is called composition of functions. But here we have compositions of linear transformation. I mean, it is almost same. There is no much difference. Let's suppose T is a linear transformation and the standard matrix is A. S is a linear transformation and the standard matrix is B. Then if they ask you that what is the standard matrix corresponding to this composition, then you tell me you're doing S first or T first. You're doing S first, right? So instead of SB, you can write VB, and then because S is corresponding to B, and then if you take whole linear transformation of this vector, or whatever this vector is, the whole vector, then you need to multiply by A, right? Then it will be ABB. So basically, whatever you are doing first, so as you are doing first, so that is why first you need to multiply by B, and then you are doing T, so you need to multiply by A. This is very easy. Let's do one question, and maybe you will get to understand more. So what they're saying, consider this linear transformation with respect to these two matrices. What is the composition? Okay. What is the matrix of this composition? Can you calculate? Can you tell me what is the answer you are getting? So you just tell me, let's suppose this is A, this is B. You just tell me what is the answer, AB or BA? First tell me this. What is the matrix associated with this composition, AB or BA? It should be AB, right? Because you are doing S first and then T. So you just need to multiply by A and then B, and then you will be getting your answer. Okay. So see, this is A, right? This is B, and the answer is this one, which is, I think, this option. Okay. So A into B. This is A, this is B, and this is the answer, right? Okay. Let's do this. For the following linear transformation, write down the corresponding standard matrix, the composition of the transformation. For this transformation, can you tell me the corresponding matrix? First, you need to tell me the matrix corresponding to this, then the matrix corresponding to this, and then they are asking compositions of the transformation. Okay. By the way, do you think that T2 of T1, something like this will make sense? Yeah, this can make sense. Uh, okay. Will this make sense or this will make sense? Just tell me, out of these two, which will make sense? T1 composition with T2 or T2 composition with T1? Make sense in the sense based on the dimension. See, T2 is saying that I can take R2 as an input, right? If T2 can take R2 as an input, then it is fine. I mean, it is okay. This kind of composition is okay because T1 is ultimately giving the R2 as output. So this is R2, this is the vector in R2. I mean, this will give the vector in R2. And then ultimately you are taking that vector and then it will give. So this is making sense. Is this making sense? So it will, T2 will give you the vector in R2, right? T2 will give the vector in R2, and then T1 cannot consume that vector. So this is not even making sense. So that is the reason that they have not even specified, right? They have not even specified that it is T1 T2 or T2 T1, because one of them is not making sense, right? It is not making sense. Let me know how many of you understood why it is not making sense. Okay, let me ask the reverse question. How many of you have not understood that why it is not making sense? You can tell me frankly. Okay, I can just quickly explain. Don't worry. Just let me know quickly. Okay, you just see this, that what I'm trying to say, that if you try to have the composition of, let's suppose, T2 and then T1, then you tell me ultimately this T1 is giving you a vector in which space, R2 or R1? So this will be in R2, right? and and this can consume, this T2 can consume R2 vector, and ultimately it will give you R2. So basically, ultimately it can consume the R2 vector, and ultimately this is also R2, right? So that's fine. But let's just see the other way around, which means T1 composition with T2 and then X. It means T1 need to consume T2X. Let's just check. T2 will give vector in R2 or R1? T2 will give final vector in R2, right? T2 will give final vector in R2. Can T1 consume the vector in R2? No, right? So T1 won't be able to consume. So that is why it is not even defined. It is not making sense. Okay. That is what I meant. Okay. So basically T2, T1 you need to find out. Now, can you do this? You can find out the matrix corresponding to T2. You can find out the matrix corresponding to T1, and then you can find out the answer. So Tejas More has given some answer. Let me just check whether this answer is correct or not. Okay, I can quickly verify. Okay, so Tejas has given this answer, 12101. Yeah, I think this is correct, right? So this is the matrix corresponding to T1, right? So there's a matrix corresponding to T1. There's a matrix corresponding to T1. There's a matrix corresponding to T2. You need to multiply um, T1 matrix and T2 matrix like this, right? Can you multiply? Tell me, is this multiplication even defined? T1 first and then T2 later. This is 2 into 3. Can you do this multiplication? This is not defined, right? This is not even defined. Okay. You want to be able to do it, even if you want to do it, right? Okay. Let's do this question. What they're saying: determine whether each of the following statements are true or false. Give a brief justification. Okay. A homogeneous linear system of two equations in three variables will always have infinitely many solutions. Two equations and three variables, which means three variables, right? And two equations. So which means this kind of matrix. It will always have the free variable, yes, because pivot can be at most two. So I think this is true, right? This is true. Okay, this is true. What about this? Any three vectors in R3 will form a basis. This is false, not any three, right? A linear system of three equations in two variables. Three equations and two variables, which means two variables, which means like this, right? Will always is always inconsistent. No. Okay, it will depend on B. Yeah, it need not to be, right? I mean, it may be because there are two vectors only in R3. Maybe it is inconsistent, but it is not always, right? It is not always. It will depend on B. The composition of two linear transformation is linear transformation. Yes, right? It is just a B or BA. Okay, it is just A, B or BA. So this is also the matrix. Okay, this is also the matrix. So this is true. Okay. So now let's just quickly have a small detour And let me quickly tell you the definition of function and these things, and then we will talk about something called as one one and onto functions, right? I mean onto and one one linear transformations. Okay. So before that, actually, just a second. I want to show you some geometric interpretations also. Okay, so I want to just share one geometric interpretation of linear transformation or the matrices. Are you able to see my screen? Okay, okay. So you can see here that this matrix A, right? So if you multiply this matrix A with any vector, let's suppose x, y, this matrix is such that it is doing minus x and y, right? So basically, I mean, this matrix is if you multiply any vector with this, then it is just doing minus x and y. So it means it is taking the x coordinate and making it minus. So if the x is, let's suppose, for example, okay, let me just take one example. Don't worry, just a second. For example, let's suppose that I take some vector. Let's suppose 1, 2. Okay. Let's suppose there is a vector 1, 2. Okay, or 2, 1 or whatever, right? Let's suppose this is 2, 1. Then after this matrix multiplication, what it will do? What is the final vector? Can anyone tell me? It will be minus 2 and 1, right? I mean, x coordinate will be minus 2, which means it will be something like this, right? It will be something like this. It will be minus 2 and 1. So you can see that every vector that you are taking, it is just a reflection with respect to y-axis, isn't it? I mean, any vector you take here, it will be just a reflection with respect to y-axis. So if it is already negative, okay, if let's suppose x was already negative, then it will make it here. I mean, it will be changing the sign of x. If x was here, then it will be doing it. If x was here, then it will be doing like this, right? So it is just a reflection. Let me know if this understood to everyone. Is this okay? Yes, right. So it is a mirror image with respect to y. So I'm just sharing one special matrix. Let's suppose then it is doing what? It is taking the mirror image with respect to y. So you see, let's suppose you have some picture which is having some pixels. For example, maybe the pixel value of every of this pixel will be something, right, between 0 to 255. So whatever is the pixel value, what it is doing, I mean, there will be the coordinates, right? I mean, everyone is having the coordinate. So for example, this is from 0 to 255 like that. So anyway, so if you understand this is the every point is a coordinate, then you can understand that okay, that every vector is getting flipped. So if you multiply by this matrix, then the final image that you are getting is something like this. So what we can do, if you want, like, I mean, we can do practicals also, like we can have the Python program where we can just import this image, and I can just show you if you multiply with this a, and then if you plot this image again, then it will be looking something like this, right? So it is just flipping. I mean, this is just one special matrix that you can say, which is doing the reflection. Now, there is some special matrix. If you multiply with this matrix, then it is basically for any vector. What it is doing, it is multiplying the final vector with 1.5, right? So this matrix is doing scaling, right? Which is also called dilation. Okay. So this matrix is just doing a scaling because it is multiplying every coordinate with 1.5. Now, similarly, let's suppose there is another matrix which is identity. So it is not doing anything, right? I mean, these are some special matrices. For example, let's suppose this is a matrix which is doing the rotation. For example, if you take 1, 2 and minus 2 and 1. So just tell me, okay, just tell me if you are having this matrix, right? Let's suppose you are having this matrix. Then if you have xy, then final vector is minus y and x, right? Now you tell me, let's suppose you have 2, 1. Then what is the final vector? 1 and, sorry, minus 1 and 2. Can you do the dot product of these two? This will be 2 into minus 1 minus 2. This is plus 2. So dot product will be 0, right? So basically these are orthogonal vector, which means xy is perpendicular to which vector? Minus y and x, right? So these two are perpendicular vectors, you can say. So basically what it is doing, for every vector, it is rotating how much? 90 degree it is rotating. I mean, it is making it perpendicular, right? It is just rotating in 90 degree. So for every vector, whatever vector you have, it is rotating 90 degree. So that is why, as you can see here, that let's suppose this was the initial. Okay, this was the initial. Then this line, you can understand like this is a line. Okay, and then ultimately you got this, right? If this was the line, then you got this like this, right? Anyway, like I'm just showing you that, okay, it is rotating 90 degrees. So there are special matrices, right? For example, if this is image, then after this matrix multiplication you will be getting this kind of image. Okay, it is rotating every vector by 90-degree. Just some special matrices I just want to share. Okay, nothing very fancy, but yeah, just wanted to share some special matrices. Okay, now let's have a small detour about the functions. Okay, what are the functions? I mean, we will not go to the very detail of these things, because that's not in the syllabus. I mean, for now at least it's not being covered in the linear algebra. But yeah, whatever is required I will just cover. Okay, some terminology I want to just tell you. So for example, let's suppose we say f is a function, right, from a to b. Then we also say that, okay, f is a function from a to b, or f map from a to b. Okay, maps from a to b, where this is called domain and this is called codomain. Okay, so basically, if I'm saying f is a function from a to b, then a is called domain and b is called codomain. Is this okay to everyone? I mean the terminology, that if it is from A to B, then this is domain, this is codomain, right? And let's suppose there is some element A that is getting mapped to B. Then what we call, if this is the case, then we say that B is an image. Okay, B is an image of A. Okay, we say B is an image of A. Then what we say, B is an image of A. Sorry, this is not that V. If you want to say, you can say under F. Okay, this is just one terminology, right? What is domain, what is codomain, like this, right? Okay, now for example, let me go to the next page. For example, let's suppose this is A, this is B, right? Tell me what is a domain. Domain is A. What is codomain? Codomain is B. Now, there is something called as range. Okay, range is something which you will say that see, every element of B might not be mapped, right? I mean, you might not be able to get every element of B. So basically, you can say that, for example, that something, only some of this, okay, some of the B will be mapped. So this some part will call range, right? This is called range. For example, let me just give you the example. If let's suppose you have a function x square, right? Does this map to every real number? Let's suppose I define a function r to r. Okay, and what is the function? Fx equal to x square, right? Now tell me, is range r, is this mapping to every real number? Then answer is no, right? Answer is no. It is only perfect squares are there, right? Perfect squares are there. No, not every number, right? Every real number. It has to be positive and positive or zero, and that too perfect square, right? Okay. So basically, I hope you understood what is range, right? So range of a function is basically that what it is actually mapping to. Okay. These are just two, three terms that I want to share. Okay, that's all. Cool. Now, for example, this is a function. These are the functions, right? This is a function like this. Okay, so I hope these definitions are clear. What is domain? Set of all things that may be input to produce some output. What is codomain? Of a function is set of all values that are potential output. It may not be output. Okay, it may not be the final output. But initially we thought that, okay, maybe it is the case, R to R. Okay, maybe it is the case. Maybe R is the final. I mean ultimately it will be mapping to R. Okay, but may not be all the values in the R. So range is something which specifically says that it is mapping to this particular set. So basically, the range of a function is a set of all things that are output. Once one knows the domain of a function, one can determine the range by applying the function on each element of the domain. Okay, so it is basically set of all things that are actually the output. Understood? Cool. So again, domain, codomain, and range. I hope these definitions are clear. In terms of the linear transformation also, you can understand that for the linear transformation, if I'm defining the linear transformation like this, then tell me if this is the case, then what is the domain? Domain is Rn, codomain is Rm, right? And what is the range? Range you can define like this: set of all images, or maybe set of all values that T gives. So basically, it says Tx where x belongs to Rn, right? This is the range. Is this okay? Now you tell me, is this Tx isn't this Tx is same as Ax? Is this Tx same as Ax? Yes, right? So this Tx, we have seen this Tx is same as Ax. So you can say that this is same as Ax, right? Can you say that range of linear transformation is nothing but, is this true or false? Let me just write it. Range of linear transformation. Okay. Is the same, is this true or false? This is true, right? I mean, for the range is nothing but a column space of A. Okay. Whatever the column space is spanning is basically that is the range. I mean, the whole column space is just a range of the linear transformation. Is this understood to everyone? That what I'm trying to say here? Let me know. How many of you have not understood this? That range of the linear transformation is nothing but the column space, because Tx range is nothing but whatever it can produce, right? Tx is nothing but Ax, right? So Ax is nothing but the in the column space. So you will say it is just a column space of A. Okay. So for example, you can see this diagram probably. This is domain, this is codomain, and range here. So let's suppose this is Rm. Range is basically the explicitly the shaded part, right? The shaded part is not the whole part, not this whole square. Okay. So range is just a shaded part. Okay. Range is just a shaded part. Okay. Wherever Tx is, right? Okay. For example, this is the matrix associated. Now T takes this. Okay. This is A T. That is fine. Okay. Now let's just see one-to-one function and on-to functions. Okay, these are the two specific type of function. We will see that, right? So what is one-to-one function? It is also very easy. It is just saying that for every element here, so it is just saying for every, I mean, for every element in a function. First, you tell me for a function to be there, if let's suppose these are the one, two, three, four element. Tell me, can this particular any particular value have multiple output? Is this possible? Is this possible in a function? Then no, right? This is not possible. I mean, if it is x square, then it is fixed that x square is for example, if for x equal to 2, it is 4, right? I mean, it is fixed, so it is not even the function. So this kind of things are not even the function. Tell me, is this a function? Is this a function? Fx equal to plus minus square root of x. Is this a function? Answer is no, right? See, plus minus square root of x is not a function. I mean, it is plus 2 or minus 2. If it is not fixed, then it is not a function, right? No. Okay. Because these are the two values. For every x, these are the two values. So these kind of things are not even the function. Okay. Now, what are the one-to-one function? It basically says that you don't have two values mapping to just one value. For example, these two values, right? The two values are not mapping to one value. Is it possible to map one value in a general function? For example, let's suppose if you have fx equal to x square. For f of 2 and for f of minus 2, what is this? Both are 4, right? Both are 4. So if it is 2 or minus 2, both are giving you 4. Now, this a function? Yes, this is a function. Why? Because, I mean, because for every input, you just have just one output. That's okay. So this is a function. That's okay. But is this a one-one function? One-one function says that for every element here, that every element here just map to one of the element. Okay. So which means that two elements here cannot map to just single element. two or more elements. So this is a function that is there, but this is not 1 1. Okay, so let me tell you the definition of 1 1. Definition of 1 1 says that if if you have, let's suppose you have here, you have multiple, elements, you have multiple elements here, then each of the element, okay, each of the element here will be mapping to, will be mapping to exactly, okay, I mean, this is the function that is there, I mean, exactly one element it will be mapping to, but each of the element here. So you can say that image of this, okay, if you if you find out the, that is called the inverse image or something. So by the way, if you say that, for if you pick each element here, then there will be just one element corresponding to it, which means mathematically I can say that if fx and fy are equal, let's suppose fy, okay, which means if two elements are mapping to the same one, is this possible? Fx and fy, can they map to the same one in the 1 1 function? Is not possible, right? This is not possible. So you will say fx equal to fy is not possible, or in other words, mathematically you will say if it is there, then x must have to be equal to y, which means two different element can't give you a single element. Anyway, we are not very much interested in the mathematical definition, but I hope the geometric definition is okay to everyone. What I'm trying to say here is that if you are having, if you are having, let's suppose this a and b c d four elements here, then here you can skip any of the element, that is fine, but here this 3, for example, this 3 cannot map to multiple elements, okay, it cannot map to d and a or like this, right? So there will be just one element. If you talk about this 3, there will be just one pre-image, okay, here you will be finding just one element, right? So basically it is 1 to 1 means that every element here will be just mapping to, there will be 1 to 1 relationship. There will be 1 to 1 relationship. Very, very easy, right? There is just 1 to 1 relationship. Can you skip one of the element here? Yes, you can definitely skip. Okay. You can definitely skip. So Tejas is saying fx equal to floor x and these kind of things. These are functions, right? See, floor x and these kind of things are function, but these are not 1 1 function. I mean, floor of x, tell me 3.2. Is this mapping to multiple outputs or just one output? Are you confused whether it is 3 or 4 or 3.5? No, this is 3, right? This is 3. Yeah, this is not 1 to 1 function. Why? Because, for example, 3.3, this is also 3, right? Multiple elements are mapping to 3. So that's why it is not 1 to 1 function. So floor is not 1 to 1 function. So 1 to 1 function is actually very easy. It is just saying that for every element will be mapping to just one element, which means this will be mapping to one element, one element, one element, one element, right? And now since it is a function, so it has to be, I mean, for the domain, if the domain is there, then it has to be like it has to give the value for every element in the domain, which means if it is 1 to 1 function, let's suppose if it is 1 to 1 function, tell me, how many minimum elements have to be there in this right part? If these are the four elements, how many minimum elements has to be there in the right part? At least four, right? At least four. Can there be five? Yes. Can there be six? Yes. Okay. I mean, that's okay. If it is in the code domain, that's okay. But it is not in the range. That's fine, right? I mean, at least four element has to be there. So 1 1 says that, okay, for every element, there is 1 1. I mean, 1 to 1 mapping, 1 to 1, 1 to 1, 1 to 1. Some element can they get left here? Yes, they can get left here. Tell me, can some element get left here? Let's suppose, is this okay? No. Why? Because for the at least function, it has to be defined for every element in the domain. Function should give some value here, some value here, like this, right? So for every element, it has to be there. So it is not even the function. If I'm leaving some of the things here, it is not even the function, right? So you can say that for 1 to 1 function, that's fine, right? I mean, everyone is mapping to just 1 1 1 1 1 1, and things can get left here. Okay. Now there is one more type of function which is called onto function. Onto function says that codomain and range are same, which means they say that that If let's suppose these are 3, 4, 5, 6, or whatever number of elements, then each element should be having the image. Okay, each element should be having the image. So which means it may be possible, but that one element is basically having mapped to two different elements. That's fine. That's fine. But each element must be having the image. Okay, that's called onto function. Each element must be having at least, let's suppose these are the 1, 2, 3, 4, 5, 6 elements here. Then how many elements should be there here? At least six, right? I mean, each element must be having one image here. Okay. Okay, so these are the definitions. Maybe you will get to know more with the examples. So, for example, the mathematical definition. Let's just quickly see. For example, if both are same, which means if two elements are mapping to the same element, can this happen in the one one? No, in the one one it cannot happen. If it is happening, it must be the same element, right? It is another way of saying it. Similarly, similarly, there exists some. If they are saying that for every b, right, in the codomain, there exists some a, okay, for which it is happening. So maybe you can understand more with the example. Let's just classify each of them as one onto neither both like this, right? Tell me, this is a one onto or something like that. So just one-to-one relationship, one-to-one relationship. Yes. So it is definitely one because one-to-one relationship. Now you also check, is this leaving out something? Since it is leaving out, so you will say it is only one, but not onto, right? Onto no, one, yes. What about this? So one relationship, okay. This. Tell me, is this one? No, right? Because two elements are mapping to same. So it is not one. Okay. So one is no. It is onto. Are you leaving out anything? No. So that's why it is onto. Tell me, are you leaving out anything? No. So that's why it is onto. Is this one? I think everyone is mapping to just single element, right? This is one. So from here you can see there is only one incoming arrow. Okay. Now you tell me, what about this? It is leaving out something. So it is not onto. It is mapping two elements. As you can see, two incoming arrow to just one thing. So that's why it is not even one. What about this? A is giving you multiple output. A is giving you multiple output, right? It is not even the function. So you can say not even the function. Okay. So just a brief detour I want to have. So you can see that this is not even the function, neither one. Okay. So these are the answers here, right? Now let's just come back to our linear transformation and let's just try to see in terms of the linear transformation I want what I want to convey. Okay. So suppose that there is a linear transformation. Can you tell me the domain, codomain, and the range of T? So what is the domain? So this is 3 into 2, right? So what is the domain? It will be R2, right? I think it will be taking vector from R2 or R3. So AX, this is the domain, right? So if this is 3 cross 2, then it will be 2 cross 1, and then final will be 3 cross 1, right? So you will say the domain is R2, codomain is R3, because finally it will give the vector in R3. What is the range? For the range, you can say it is a column space of A. I mean, you can find out the basis vectors. Are these vectors linearly independent? Yes. So you can say that span of 0, 1, 2, 1, 1 minus 1, right? These two vectors. You can say this is the range. Okay. You can find out this, right? 0, 1 is nothing but this vector, right? This is nothing but 1, 1 minus. Is this fine to everyone? Okay. So range is nothing but a column space, which is a plane, right? Because these are just two vectors. So and both are linearly independent. Plane, which is in R3. Okay. Now let's just see one to one. I mean, function we have seen, but let's just also see one to one transformation. Okay. I mean, both are the same thing, but just for the sake of completion, I'm just reading out this definition. A transformation is one to one if different vectors in Rn map to the different vectors in Rm, right? In other words, for every vector B in Rm, the equation has at most one solution. So you will say that if we are having Ax equal to B, or maybe Tx equal to B, right? Tx or Ta. Okay, Tx equal to B. Now, for every B, if it is one to one, then for every B, there will be exactly one or at most one. Can this be one one? Can this be one one? Not one one, right? Not one one. Okay. If this is B, let's suppose only one is there, then yes, this is one one. If no one is mapping to B, then also that's fine. I mean, one doesn't say that it should map to something, right? Then also it's fine. So if no one is mapping to B, then also it's fine. So basically, you will say if let's suppose no B, no X is mapping, then also it is fine, isn't it? So this is also one one. So I will say that for Tx equal to B, for every B, there is at most one solution, right? So for every B, at most one solution. Is this fine to everyone? Let me know. Is this definition fine? We will do many examples. I think more than 20 examples, or I don't have the count, but I think we will do many examples. Okay, more than 15 examples to understand this. But for now, just let me know the basics are fine or not. That if I'm saying Tx equal to B have to be 1 1, then it means what? That for every B, it cannot map to obviously two. I mean, for every B there cannot be two solutions. Either there is one solution, or there is no solution, right? So at most one solution. Is this fine? In other words, for every B, at most one solution. Let me know if this line is fine. Okay. Now, if that is the case, now you tell me, can I say, if that is the case, can I say that, or you just tell me that what should be the conditions? What should be the conditions? Yes, Ajay just told me what should be the conditions of, columns of A. So it means if we are having Ax equal to B and you want at most one solution, then what does this mean? It means columns of A should be linearly independent, right? Then it is one to one. Okay. Now let's just see on to, or maybe we can, before I see the on to, let's just do some easy examples so that you can get to understand more about one to one, and then we will see on to definition with respect to linear transformation. Okay. Let's suppose there's a question where you have the linear transformation something like this. U is this, then Tu is this. Okay. Okay, you can, I think, okay, you can ignore the first line. Maybe I wanted to ask to you. Okay. So you can calculate TU, that's fine. Let's just go to the second question. Let B be this, okay? 757. Suppose this is 757. Then find the vector V in R2 such that TV equal to B. Okay. So what they're saying that AX equal to B, you find the solutions of X. Are there multiple solutions? That's what also they're asking. So which means they are saying that for 101, 111, okay, into X equal to B is 757. Tell me, will there be multiple solutions? You can tell directly. Will there be multiple solutions? No, right? There will be either unique solution or no solution. Okay. So you just tell me, is this one function, one linear transformation? Yes, this will be one linear transformation, right? So this will be one linear transformation, one to one linear transformation. Okay. Why? Because because columns of A are linearly independent, right? That is why for every B, either there is no solution or there is at most one solution. But in this case, you can find out, okay, I mean, you can solve this equation. What do you think? I think it will be 5 multiple. It will be 2 multiple, right? Yeah. So multiple because it is 0. So that's why you can say it is 2 into this. It is 5 into this, right? Okay. Yeah. Okay. So there is just one solution. Okay. Now let's just do this quickly. What they're saying is there a C in R3 such that there is more than one V? You can just quickly tell me. Will there be for any C will there be multiple solutions in this case? What do you think? Will there be multiple solutions? No, right? No, since columns of A are linearly independent. Find C such that there is no V. Okay, so they are saying you just tell me some C. There is no V. Is this really the case? Yes, that could be the case because is it spanning R3? See, they are saying, can you tell me some C? Okay, some C there such that there is no solution. So yeah, that could be the case. If it is not spanning, then maybe you can just tell, right? Some C which is linearly independent of this also and this also. Maybe you can just try to tell. Um, if you multiply by 2 here, then you will be getting 2, 0, 2, and this is 2, 2, 2. Maybe 203 should work, right? It is neither multiple of this nor it is multiple of this. But can this be obtained with both? Just quickly see. If you want, let's suppose, for example, it is 1. So I think it can't be 213. Okay. So it can't be obtained with both. Because if you want one here, you need to take one multiple of this. And then if you're taking one multiple of this, then two multiple of this. Okay, this is there. Two multiple of this, and one multiple. No, okay, we are not getting this because you will be getting 3 now. Okay. So you can have any other vector also. Find C such that this is inconsistent. Find C that is not in the column space. We could draw a picture and notice that C equal to 1, 2, 3. Then our matrix will to this, which is inconsistent. Anyway, so you can find some C. I mean, they will give the options, and with the option, you can at least find out that okay, which of the option is not having the solution, right? Okay, just tell me this one to one. Just quickly tell me. This is yes. Okay. Let's just see this. Is this one to one? If not, then find two vectors such that they are mapping to the same thing. Okay. So is this one to one? No, right? No, because columns are right. So what are the two vectors? I think this is forming the basis. You can take maybe 2, 2, right? If you take 2, 2, can you tell me the multiple solutions of x? See, 2, 2 is just a multiple of this. So maybe you can say 0 to 0. This is the solution, right? 0 to 0 is a solution because it is directly a multiple of this. And also this can be obtained like this, right? So you can say 202, 202, right? These are the two solutions of 2, 2. right? I just observed that okay, this is a basis, this is forming a, I mean, this is a standard basis. So I just observed this, and then I took some multiple of this. Okay, this was my quick observation. Based on that, I did this. Okay. So as you can see here, this range is shaded part. Okay, the shaded part is the range, and range is not exactly equal to codomain. So for example, codomain is this, and range is not exactly equal to codomain, right? And now every vector here is mapping to just, I mean, like inverse, you can say inverse mapping to just one of the element, right? One of the element in the domain. So that's why it is one to one, right? It is one one. But for example, if you see this, this vector is mapping to two vectors here. So this is not one one. Okay. Now let's just see more examples. So let's just see the definition of onto, okay, with respect to the linear transformation. Now, what is onto? It doesn't leave anything here, right? It doesn't leave anything here. So if ax equal to b, when it will be onto? Whenever a is spanning the whole space, right? Whenever a is spanning the whole space, then only you have solution for every b. So you can say that has at least one solution, right? At least one solution. Earlier we said like at most one solution. Now we are saying at least one solution. So it doesn't really care that this has multiple solution or not. It is just saying at least it should be mapping to someone. So at least one solution. See, earlier we said, okay, for one to one, what we said? We said that okay, if there are vectors here, then this should map to at most one, right? At most one. If we are saying that at most one solution, then we are saying it is one to one. And if we are saying that at least one solution, which means there could be multiple solutions for this, but yeah, at least one solution, right? If we are saying at least one solution, then on to. Okay. Don't worry. You don't need to remember this. I mean, with the practice and these things, it will be more clear. Now, on to basically means you don't leave anything here, right? You don't leave anything here, which means range and codomain both are same. So here, if the whole thing is codomain, then the whole thing is also shaded part, which is range. Okay. So that's why it is on to. Now, here if the range is this much only, okay, if range is only the shaded part this much only, this is not on to, right? Range is just a line or subspace in, let's suppose, Rm, right? Then it is not onto. Okay. This is not onto, and this is onto. Understood? Now tell me, is this onto? How to identify if it is onto? You need to check whether Ax equal to B has, I mean, it is consistent for every B, right? Always has the solution. Does this always have the solution? I think there's a basis here, right? You need to have two linearly independent vectors. So yes. So you can say two linearly independent vectors in R2, right? Okay. Tell me if it is onto or not. Can this span R3? Can this whole thing span R3? Never, right? So this whole thing can never span R3. So this is never not onto. Okay. If not, then find a vector such that there does not exist a solution. Okay. So which one is not having the solution? I think here you will be, having everything here, but here it is just, let's suppose you have 2 3, then you need to multiply 2 and then 3 here. But if you're multiplying 2, then it will be automatically 2, but let's suppose it is 4 or 5 or something, right? Okay, right. So this is not having the solution. How I find out? I just observe that okay, this is seeming like the standard basis or something. So if you are writing 2 3, then you have to multiply 2 here, you have to multiply 3 here. If you do so, then it will be 2 only, but you can have something like 5 or something, right? Okay. Okay, let's just see this question. Which of the following is or are true? A transformation T is 1 to 1 if Tx equal to B has at most one solution. Okay, just assume this T is from Rn to Rm. At most one solution, maybe no solution. Yeah, that is I think true, right? So this A is true. What about this? A transformation T is onto that has at least one solution. I think that's also fine because that's what we want in onto, that at least one solution, because it, I mean, one of this may map to multiple. That's okay, but I want everyone to cover. So yeah, at least one solution. Yeah, that's good. A matrix transformation with respect with a matrix transformation with matrix A is 1 to 1 if and only if the columns of A are linearly independent. If and only if A has pivot in every column. Yes, right. Linearly independent column should be there. This is true. A matrix transformation onto if and only if columns of A span Rm. Yeah, Rm is the final thing. Okay. R, if they're spanning Rm, then then it is true, right? If and only if A has pivot in every row. I mean, you can check this. Okay, I will tell you. So basically, is this fine that A is spanning? If the columns is spanning Rm, then it is onto because it is covering everything. And then in that case, you will automatically be having pivot in every row. Why? Let's just check. See, let's suppose this is m into n, right? Which means it takes from Rn and gives to Rm. Okay, in terms of transformation, this is like this, and matrix is m into n. Okay. Now, if this is m rows and n columns, so m rows, so this is in Rm, right? Okay. If these columns are spanning Rm, then we need to check whether the every row is having the pivot or not. So this is easy to check. I think if the columns are spanning Rm, then you need m linearly independent columns, right? Then only they can span Rm. If you have m linearly independent columns, then m linearly independent rows also, right? So if there are m rows, then everyone will be having the pivot, right? Okay. So can you do this question as a homework? I have the answer on the next page. Okay. Answer I have then on the next page. They're asking that which one is one to one on to both, neither, like this. Can you do this as a homework? Tell me. Is this okay? Okay. Answer is on the next page. Okay. Don't worry. What they're saying, let's just see. Let T be a linear transformation whose standard matrix A is this. Does T map to R4 onto R3? Is this onto or one to one? That's what they're asking. For the onto, you need to span whole R3. I think you can span whole R3. So it is onto. This is onto is there. What about one to one? Are they linearly independent? Okay, they are not linearly independent. I mean, this is in the row echelon form, as you can see, and these are not linearly independent, right? So not all columns are linearly independent. So not R2. Sorry, not one to one. Okay, let's just check this. Okay, you can do this as also homework, right? Like answer is in the next page, so they're asking just like this. Okay, just try to do this as an homework. Okay, so here also answer is on the next page. Do you want to try this also as an homework? Let me know. This is interesting question. If you want, I can solve it tomorrow. But if you want, you can also try it once and then we can solve it. Okay. So answer is on the next page. Don't worry. Just try this also. Right. Okay. Now let's just do this question. What they're saying. Let A be the square matrix Tx equal to x. Which of the following guarantee that T is onto? Which of the following guarantee? Tell me. T is 1 1. Does this guarantee you that it is onto? No, obviously no. Ax equal to 0 is consistent. For 0, Ax equal to 0 is, I think, always consistent, right? For x equal to 0, it is consistent. Column space of A is actually nothing but the whole Rn. It is a square matrix, assuming, okay, it is n cross n. The column space is spanning the whole space. So I think it will guarantee, right? There is a transformation U such that, uh, yeah, this is interesting. So they are saying that there is a transformation U such that you take the transformation. I mean, you have, I mean, you can say that there is something called inverse function. Okay. For every x, if you take that transformation, then you take t, then you will be getting x again. What does this mean? See here that if you are having, let's suppose ux is actually, let's suppose b, right? So it will be, it means a and b are inverse of each other, right? So what they're saying is that, let's just try to understand. So it is a square matrix, by the way. Okay. Uh, so this is Rn. So let me go to the next page. Let's suppose both are Rn. This is also Rn. Okay. T composition of U of x is giving you x. So let's suppose here what I'm trying to say onto, right? So they are saying onto. Okay. So here you are basically covering everything here, right? If there is a transformation that can, um, let's suppose this is x. So what is the meaning of this u of x composition of with t? Yeah, inverse must exist. So Ajay is saying we have n linearly independent column determinant of node 0, therefore inverse exist. No, I want to check whether does this mean that, okay, so basically we want to check, does this mean that function is onto? Okay, so let's do one thing. Maybe you can just also try this. I will also see. So this is related to some inverse property, right? Inverse property of the functions. And then after the inverse property and these things, it should be very obvious. So I will do one thing. I will just check the inverse property and then we'll solve this tomorrow, right? And also you can just check about this option A because the given matrix is square matrix. So in that case, if it is 1 to 1, then does this guarantee that onto? Do you want to check this now? Because this is a square matrix. So see, if it is a square matrix, it means, or maybe in terms of the matrix, I can tell you this A is n cross n, right? If it is 1 to 1, then what does this mean? It means the columns are linearly independent, right? These are linearly independent columns, right? Does this mean it is spanning the Rn? Yes, it is spanning the Rn, right? So basically, for the square matrix, if it is one to one, then it is onto also. I mean, it is nice interpretation that you can see. So that's why if it is one to one, this is onto also. Okay. And this is something which relates to inverse property. I will just tell you tomorrow. You can also try this, right? You can also try this as an homework, and then we will just solve this tomorrow. Okay, great. So now let's just solve more questions. Let's see this question. So what they're saying, domain and these things they're asking. I think okay, this is easy question. I have that solution on the next page. Domain, codomain, these things they're asking, right? Okay, let's do this question. So what they're saying, it's a linear transformation with a standard matrix A, and suppose the range of T has bases containing of three vectors. So what is range? Column space of A is basically column space of A means rank of A basically you can say. I mean rank of A is just three. Rank of A is just three. Then what they're asking? What is the nullity of A? Okay, just tell me the nullity of A. Age seven. This is taking from R7. Okay, age 7 to 9 or 9 to 7. Tell me. Age 9 to 7, right? Because it is taking from R7, right? So that's why it is 7 should be here. So number of columns are 7. So can you tell me the nullity or dimension of null space of A? It is 9 minus, sorry, 7 minus 3, right? It is a good question, I think. Okay, 4 should be the answer. Okay. Now let's just solve this. Suppose that A is 7 cross 5 matrix, the null space of A is line. It means, null space of A is line means it is just having nullity is just one. Okay, one vector. Nullity is just one. Say that T is a matrix transformation like this. Which of the following must be true about range of T? Okay. So range of T means column space of A. Okay. So can you tell me column space? I mean dimension of column space? It is it is 7 is the number of rows, 5 is the number of columns, right? So 5 minus 1. I think this is 4. So this is dimensional subspace, but is this in R7 or R5? The column space is in R7 or R5? It is in R7, right? So that's why I think A is the correct answer here. Okay. Four dimensional subspace of R7, right? This is also a good question. I mean, these are, I can say these are the potential gate DA questions in the sense that they can anytime ask these type of easy questions. Okay, linear transformation is one thing which they have not asked last year, but it is very potential thing that they may ask, right? Because it is very much necessary for to understand linear algebra. Okay, for any linear algebra course, I can say is incomplete without linear transformation and change of basis. These kind of basic topics. Okay. You can try this as an homework. This is easy question. I think answer is on the next page. Okay, solution is on the next page. You can try this as an homework, right? This is solution. Okay, so these are the questions which you can try. Maybe. Can you try all of these questions? Because all of these questions have the solution, right? On the next page, there is a solution. So I think there will be too much of homework you can do. Okay. So all of these questions has a solution on the next page. So you can try. So this is again the solution. This is the solution. I mean, these are actually the similar type of questions, so that's why I'm not solving, right? Okay. Now let's just start a very new and important. I don't know if it is very important or not, but yeah, it is important to understand at least, right? The linear transformation with respect to a basis. So we have seen linear transformation. Okay. I mean, general linear transformation. For example, let's just take some linear transformation from any of the question. For example, okay, or let's just take just one random linear transformation. For example, let's suppose t of x y. Let's suppose we have seen that this is the linear transformation, right? X plus y, x minus y. Okay. Now actually people are, the mathematicians are too greedy. So what they want, they just don't want the linear transformation. They also want the linear transformation with respect to some basis. What do I mean by that? Let's suppose T is a linear transformation from input R2 to R2, right? And how do you define T? Maybe you can say that T is defined like this, right? T is defined like this. Now, what I want, I don't want the standard matrix of T. I want some other matrix of T. Okay. Which means, let's suppose here in this R2, I have some basis. I mean, B1, B2, let's suppose some basis. Okay. In R2. And there is one more basis. Let's suppose W1, W2. Okay. Let's suppose these are the basis of R2. Right. So what I want, the objective is here that I don't only want this linear transformation. I want to do something like this, that I want something like this. See, I want that my input, okay, input vector, I want input basis, or you can say input basis. I want that to be V1, V2, okay, and the output basis, I want to be W1, W2, and linear transformation also. So what do I mean by that? I mean to say following. See, I mean to say this. So I want multiple things to do at the same time. Okay, what are those things? Let me just tell you. I want to do these things. So one is that given vector will be not in the standard basis anymore. Okay, the given vector will be in this basis, and I will take that vector. Let's suppose this is okay. Let's suppose this is B1. This is B2. Okay. Let's suppose the given vector is in B1 basis. I will take that vector, will multiply with some matrix M. This matrix will do the transformation. Okay, and also the transform vector will get changed to the basis B2, which means that finally whatever I get, okay, finally whatever I get, which is a transformation of X, I don't just want the transformation, I want that to be in the B2. This is my objective and I want to find M. See, till now, we have been doing something like this. Okay. T of X equal to M of X or A of X. Is this fine to everyone? This is till now, right? Till now. Is this fine? At least this is fine, right? But now the things are little changed. Now they are saying that the vector that I want to give you, not on the standard basis, I will give in some my particular basis, let's suppose B1. And the vector finally I'm expecting after the transformation, I'm expecting the vector in B2. Okay. I want that matrix which can perform all of this. Okay. See, you notice one thing here. Inside the transformation, you always have the standard coordinate. Okay. Which means, I mean, even writing this is wrong. Okay. T of B1. We don't have something like this. Inside the transformation, you always have, see, this is plus minus something like that, right? These are the plus minus. So this is just a standard. Okay. This is a standard form, which means inside the transformation, you have just X, and what you want finally the X to be in the transform vector to be in the V2. So for example, what I mean to say, let's suppose X is given to you as 2, 3. Okay. Then how does this X fit here? You will say that first you will be calculating T of X. What it will be? It will be uh I think X plus Y, X minus Y, right? So it will be 5 and minus 1, isn't it? You will be calculating T of X, 5 and minus 1. And then this is T of X. Then you need to calculate T of X of B2, right? Then you need to calculate T of X of B2. I mean, the coordinates of this with respect to B2. And And once you calculate this, you also have to calculate the coordinate of x if it is not given. If it is given, then it is great. But if it is not given, then you have to calculate the coordinate of x with respect to x b1 also. And you put it here, right? With respect to b1, you put it here. With respect to b1, you put it here, and then you calculate all of this. So, what do I mean? Let's just do one example, and probably it will be more clear. For example, let's just say this. Okay. So here, the let's suppose the input and output basis is same, which is just b. Okay. So suppose you take some vector, right? Let's suppose that uh, you take some vector, maybe v, in the standard basis. So currently you will say that t of, or maybe x equal to, or maybe they have defined it L. Okay, L of x equal to, let's suppose some matrix A of x. Okay, I mean all of this is in standard basis, right? Currently all of this is in standard basis, but that's not what I want. My objective is that my input will be in the basis B, and output also, let's suppose, should be in the basis B. Okay, input and output both should be in the same basis. Okay, so this is my objective. Now, Aditya, let me just complete, and then after that we can have a little break. Okay. So let's just complete this example. So what do I mean by that? That input and output will be in the specific basis. So currently, let's suppose you take any vector x. So what does this mean? This x is in the standard basis, or this in basis b1? If I'm writing with this notation, this is in standard basis, right? Now you tell me what is the relationship between the standard basis and, let's suppose, x in the b1. You need to multiply b1 here. Tell me on the right hand side or left hand side. Somewhere you need to multiply b1 to make it complete on the right hand side, right? Okay, so this is the relationship between x and x of b1. See, this is what we have been doing till now, right? Doing till now. But here they are asking something else. Here they are asking something else. That is what we want to figure it out. So here they are saying that this is okay. I mean, there is nothing wrong with this. Here they are saying we want something else. Let's just see that what they want. So you just substitute, for example, for now, you just substitute this x with b1, x of b1. Is this okay to everyone? And age here as it is. Okay, age here as it is. Right? And finally, you have some transform vector. Let's suppose this is v. Finally, you have some transform vector. That is also in the, you can say, in the standard basis, right? This is a transform vector in the standard basis. This is what we have been doing till now. Okay. Now you also tell me the relationship between B and, let's suppose, B1, B of X, B1 and this B in representation of B1, right? So I hope this is also fine to everyone. So I'm also substituting the same thing. So let me also substitute here instead of B, B1, B of B1. Is this fine to everyone? Is this equation and this equation fine to everyone? Let me know. Are these two equations fine? See, from the change of basis, you should be able to understand that these two equations are okay, right? I mean, change of basis that particular lecture can tell you that these two equations are easy and okay, right? Cool. Now, if you want only this on left hand side, so let's just take only this on the left hand side. Then what should be there? It should be b1 inverse a b1, and then x in b1. Is this okay to everyone? Okay. Now, actually, that was my goal, in the sense that my goal was that I wanted, okay, I wanted some metrics which do not take the input in the standard basis. It takes, let's suppose, the matrix M. It takes the input in the B1 basis, and then do the transformation, and then finally whatever it is giving you, that vector is in the B1 basis. So finally I found my M, because that was my aim basically. Right? So what is the aim? What is the M? M is nothing but M is nothing but B1 inverse A B1, right? So can anyone tell me in terms of words, in terms of English, that what does this M do? You can unmute yourself, and if you like, you can just tell me what does this M do. Okay. Anyone wants to speak? So no, now you can unmute, I think. Okay, sorry. Now you can unmute, right?
It takes input in basis B1 and gives and transforms it.
Yes. So M takes a vector in B1, transform it, and gives back in B1, right? So it takes a vector in B1, also does the transformation. It is not just a change of basis. It is also doing the transformation, and it is giving you a vector in B1 itself. If the transformation is identical, or the transformation is, you can say, the identity matrix. Okay. If this transformation is just identity matrix, then it will be something like change of basis if this is B1 and B2. Okay, I will talk about it later on, but that's fine. So let's just do one quick example. Okay. One quick example. Just tell me, let's suppose there is some transformation. Okay. There's some transformation. Let's not even worry about this transformation, which means it could be anything: x plus y minus x, or anything. Okay. Let's suppose there is some transformation. Let's not even worry whatever this transformation, but let's just only worry about input and output basis. Let's suppose there's an input basis which is B1, there's an output basis. Now let's suppose this time this is different. Let's suppose this is B2. My goal is that I want a matrix. Okay, let me just tell you my goal. I want a matrix that takes the vector in B1 basis, do transformation, and gives the vector in B2 basis. Okay, let's suppose this is my aim. Now what will I do? Let's just first write, the usual equation. What is the usual equation? You will say, let's suppose there's a matrix A associated with this. So V equal to AX, right? Here X is in the standard basis. A is corresponding to this transformation. And it is giving in which basis it is giving? Can anyone tell me? It is giving in the standard basis, right? So it is my usual equation. Now this X input I want in B1. So let me just write this way. X equal to B1 X B1. Is this fine to everyone? And this V equal to B2 VV2. Is this also fine to everyone? I hope these two equations are fine. Now you just substitute these values. This will be V2 V B2 equal to A B1. Or actually, I want you people to do it. Okay. I mean, I just spend 1 or 2 minutes and just try to do it. I want M such that it perform my goal. I want something like this. Okay, let me just write the final equation. I want something like this. You just need to tell me what is that something. You just need to tell me the value of m. Okay, you just need to tell me the value of m. Because x, that is why we call it standard matrix, right? Standard matrix. Okay, if you're not talking about any basis, then we call it a standard matrix, which only does a transformation in the standard basis. Okay, but if you introduce basis, then you have to do some other manipulations. So yeah, I think most of you guys are correct. So here it will be just, one line of uh, one line of the equation will be there. So it will be, I think, b2. Now m will be, from here you can say, m is nothing but mm, m is nothing but b2 inverse a b1, right? Okay. So now I mean, I will tell you one other way also, intuitive way also, but at least now that, let's suppose you don't have one more way that I will tell you, but at least if someone asks you that, can you find the matrix that does the transformation takes the input from another basis, does the transformation and gives you the input from another basis, then you have that, right? You have that. Okay. Now you tell me, let's suppose just one more last thing. Let's suppose x, I want this x that is in B1, right? I want to convert x in B2. Can you tell me what is the matrix which I need to multiply here? What is the matrix? I can first multiply B1, I think, right? I can first multiply B1 to get the standard form and then B2 inverse, right? I think this multiplication will give you this, right? Is this okay to everyone? This is change of basis matrix. Let me know if that is okay, or should I explain this more, right? Now, if your linear transformation is, let's suppose, not doing anything, which means if it is identity matrix, then isn't it just changing the basis b1 and b2 inverse, which is same as the change of basis matrix, right? I mean, we will talk more about it, but intuitively, can you just just relate it for a minute, and then we will talk more about it, obviously. But I'm just telling you if it is okay. Okay. See here, if A is identity, then your linear transformation is nothing, right? I mean, it is not doing anything. So if it is not doing anything, then it is if it is a b1 to b2, then it is just a change of basis, right? It is just a change of basis matrix if it is not doing anything. Okay, if it is identity. Anyway, but is this calculation fine to everyone? This is more important for now. Is this calculation fine? What I'm trying to say, that now you have your matrix which do certain things. Takes the vector in B1, transform and gives the vector in B2. Okay. So now suppose M is such matrix which does this, okay, which basically transform, take the vector in b1, gives the vector in b2, then we represent like this, right? We represent like this, and which is nothing but b2 inverse a b1, where a is corresponding standard matrix. ये एक रिप्रेजेंटेशन है. Okay, this is just a notation. Okay, this is how we will denote. So tell me, is this a matrix or a vector? It is a it is a matrix. It is a matrix actually. Okay, it is a matrix which takes from b1, transform and gives to b2. Okay, so it is just a notation. Tell me, is this a matrix or vector? This is a vector. Okay, this is a vector. Okay, these are the notations I'm just telling you. This is a vector. But if I write like this, then people say it is a, I mean, this is a notation, and this is just a notation for the for my m. Okay, which is clear that what it is doing, takes b1, I mean, takes the vector in b1, transform and gives the vector in b2. Okay, this is a matrix. Understood? Anyway, just tell me, this is a vector or matrix? This is a transformation of x, and which is a vector. Again, this is a vector, right? This is just a vector. Okay. Anyway, cool. Understood? Now you know that, okay, how to I mean, how to approach from one to another. Now let's just solve this. Okay, let's just solve this question. Let's suppose I want to find a matrix which does this transformation and takes from input b and gives from output b itself. Okay, I mean, b1 and b2 here are the same. Do you want to do this? Just try it. Okay. So see, the question is that what is the matrix that does this transformation, but it does not take the arbitrary, I mean, from any basis. It takes from this basis. Input is this basis. Output is the same basis. So basically, you can say your usual equation is something like this. Okay, L or T, whatever. So let's suppose ax equal to b. This is your usual equation, right? You want in b, right? So you will say this b is nothing but b of b into b. Okay, and then that is equal to a of b into x of b, right? From here you can write b of b equal to b inverse ab x of b, right? So this is the matrix I just asked you. Okay, that takes input from the basis b, and then do the transformation and then reverse it. Okay, and give the output in the basis b. So it is just a computation, right? Has anyone calculated the answer? Okay, b inverse ab, maybe I think that is there. If you do this b inverse lb or ab, then okay, the answer also I don't have, but yeah, you can calculate it, right? So this will be your final answer. Okay, so that is how basically you can do the transformation also, and change of basis also. I mean, you can basically change the basis, get the transformation, these things, right? Okay, Tejas is giving some answer. I'm not sure if the calculation is correct. Tejas, you did it yourself or online some calculation you did it? Okay, so most probably it might be correct, but that's fine. Okay, you can just verify, right? This is the final answer that Tejas is giving you. But the most important thing is that have you got to know that how to calculate this M? Okay, okay. Let's just do one thing. Can you do as an homework if you want, or maybe we can do it now. Can you do one thing? Can you also verify whether it is correct or not? Which means, which means you can take some vector x, maybe 1 2 3. This is x. Just find out. Okay, just find out x in the basis b. Okay, whatever this is, then can anyone tell me what is b of b? M into this x or x of b. M is taking x or x of b. M is taking x of b, right? I mean, that's how M is defined. It takes x of b, right? So this is the equation. Okay. So what you can do, you can take this x, okay, do the transformation. I mean, you just find out as, okay, let me just tell you. So there are two ways to get VB, right? What is the method one? You can say, just if you have got b, if you have got m, you can directly do like this, right? Okay, this is one way. Another way is you can do the other procedure, which is that you have your x, right? What is that? 1 2 3. You just find out a transformation of this x, maybe L of x. Okay, you just find out this, and then this is easy to find out, and then represent that in b, right? This should be this final, this should be same as, this should be b of b. Basically, what I mean to say, you just find out this b of b using this m. This is one way. Another way is that if you have x, right? You have x, then you can find out the transformation, and then ultimately you want the transform vector into the b, right? So ultimately you just find out the coordinates of the transform vector in the basis b, and then this should be same as this b of b. Okay, remember, this is xb, this is not x, this is not x. M doesn't take x, M takes xb. You may be having x, that's fine. You need to calculate first xb, and then you need to multiply, then you will be getting this bb. And and there is another way where you have this x, let's suppose directly you find out the transformation. If this is in the standard form, you just find out the transformation. Inside the transformation, always remember, this cannot be x of b or something. This will always be in the standard basis. Okay, inside the transformation. Later on, whatever you want to do after the transformation, you can do anything, but inside the transformation, always remember, it cannot be x of b, right? So you take this x, you find out the transformation, and then you find out the coordinates of these. This should be same as this particular v. Okay, so let's just do one thing. Maybe we can stop the class for today, and tomorrow we will resume this topic. Tomorrow I will tell you one more very nice intuition, that that how to calculate this m. Okay, very nice intuition for this m. I mean, today we have seen mathematically. Tomorrow we will see little intuition about it, right? And then what we will be doing, we will be basically finding out, let's suppose you can say that will be the method 3 or something. Okay, let's suppose that is method 3. Using that also we can find out m. Okay, so we will be finding out m using one more method, and then we can compare all of these three methods, and all of these three methods will be same. Okay, we can do exercise tomorrow, which means like we can actually calculate it. I will not give as an homework for the calculation. Even I will be having the printed slide where the answers of these are directly there. I mean, we do not need to calculate the inverse and all. I will pre-calculate it and I will put it in the slides, right? But today I want to just convey a little idea here, that you can do multiple things, right? Is this idea a little bit clear? Okay, don't worry if it is seeming tough, but it will be very clear later on when we do many examples, right? As you can see in the slides, we have many examples. For example, this question, right? This question where the basis, this is input basis, probably this is output basis, right? Okay, this question, for example, this question. So here the bases are these. This is one basis. For example, yeah, this is one basis, D is one basis, E is another basis. So input and output basis could be different, right? For example, like there are many questions we will be doing. Okay, and I'm sure after all of these questions, see here, after all of these questions, it will be very clear that what I want to ask. But is this little bit understood that what is the idea here? We don't just want the transformation. Okay, this is okay, but I want a matrix that has input basis, and finally it is giving you in the output basis some other basis, the transform vector in some other basis. I mean, people want to do all of this with just one matrix, and we can do it because this is just a matrix multiplication at the end of the day. Okay, see, this topic actually, let me just tell you, this topic, if you directly try to study from anywhere, then it will be very difficult, because the notations and these things will be very confusing. So I want to make sure that this is at least understood, that what is our goal, and this particular method, whatever we have today told you, right, that how to find this m. I think you people only told this m. So this particular example that we have done, so here this m, most of you have given the correct answer, that this m is this, right? So I'm confident that now you know that how to calculate the sum. It is just that we just need to have more feel about it, more intuition about it, more examples about it, right? So we will do it tomorrow. Okay, cool. And then we will be having, one homework for all of this, or maybe we can directly have a quiz, whatever suits. Maybe we can first have the homework and then we can have the quiz for linear transformation basis and vector space, right? Okay, I mean, I think vector space already has had the homework. We can have a video solution of that, and then for linear transformation and change of basis, we will be having one more homework, right? One or two more homeworks. Yes, definitely. Okay. So this Wednesday we will be having quiz, as you know, from linear algebra syllabus, which is GATE CSE syllabus. And then before the Wednesday, I will try to put a homework for this change of basis and linear transformation, right? Because these are very important and very nice also. एक्चुअली इतना टफ नहीं है जितना मतलब तुम लोगों को लग रहा है, या फिर तुम लोग, मुझे पता है तुम लोगों को समझ में आता है, लेकिन यू डोंट से इट, मतलब ये आदत हो गई है कि कि बोलेंगे नहीं तो अच्छा होगा। दैट इज फाइन, मतलब थोड़ा बहुत समझ में आ रहा है ना शुरू में, वो ही इंपॉर्टेंट है। ठीक है, धीरे धीरे सब कुछ क्लियर हो जाएगा, बट इनिशियली थोड़ा थोड़ा समझ में आएगा, तो इवेंचुअली इट विल बी अंडरस्टूड, राइट? मतलब एट फर्स्ट इट माइट नॉट बी वेरी वेरी क्लियर, बट इवेंचुअली इट विल मेक सेंस। ठीक है, सो जस्ट टेल मी कि इतना समझ में आया कि व्हाट वाज अवर गोल, कि इनपुट एंड आउटपुट बेसिस होते हैं, एंड अवर गोल इज टू कंबाइन थ्री थिंग्स। ट्रांसफॉर्मेशन भी करना है, इनपुट बेसिस से लेना है कोई वेक्टर, ट्रांसफॉर्म करना है एंड आउटपुट बेसिस में देना है। दिस इज अवर गोल, राइट? एंड वी वांट टू अचीव दैट गोल विद जस्ट वन मैट्रिक्स। सो हाउ टू कैलकुलेट दैट मैट्रिक्स? Theoretically, we have seen that. Now, tomorrow we will do more examples. Okay, cool. So, thank you, everyone. Thank you so much. Take care. Bye bye.